All right, so where we were at the end last time, just to remind ourselves, so the recap. So we were talking at the end last time, we were saying that we could easily define the idea of a pushout. So we define pushouts as a higher inductive definition, so we can write it like that. Where in the fairly evident way, if we want to define, if we have a diagram, we have like C, we have maybe F going to A and G going to B, then we can define their pushout by having an inclusion from A into, well, we need a name for whatever it is, so the name that's suggested in the book is this one, that's fine. And we have an in right, which would go here. So what we're thinking of this as, and then we had what is called in the book glue, which says that, well, for every C and C, because we have this sort of, remember, we kind of think of this as a way of drawing a diagram in A and B, and we want to form essentially, so over here we're starting out by forming their sum, except that we want to amalgamate the parts that are in the images. So we end up putting some equations that say that we want to end up having that the in left, let's see, the, what do I want to say here? In left of F of C, because that should go to the left, I hope, if I did everything right. Last time I got confused. Should be equal in the target that we're putting here to the in right of G of C, okay, for all the C's in C, and we consider that to be a higher inductive definition. So remember, that's what we did. And I was telling you, I was pointing out the analogy with the construction that you do in sets when you say that, well, if these were an ordinary blackboard mathematics that we normally do, and these are just plain sets, then we would just define it as a quotient we could define the pushout as a quotient of the sum, and that's kind of what we're doing here. In fact, that's going to lead to the next point, which is how we get to quotients. So we can do that. So we did that, but what we pointed out is that we can then observe that this, what I call the suspension of A, and this notation can be defined as the, well, this notation is kind of okay here, because what it really means is the pushout of the unique maps, okay, that go from A to 1 and A to 1. In other words, you're starting with A to 1 and A to 1, okay, which are, these things are given uniquely, and then you're forming the pushout here, which is going to be the suspension, and we talked about that. Okay, and then what I forgot to mention, and then there are other things, but that's an example. And so one corollary of this is that, which is kind of useful, is to do with the n-types. So we did that as a remark. So the idea is that, I can just put it informally, we can even say that the push, I'll put it like this, the pushout of two sets needn't be a set. By which I mean in the H sets, if you want to use that to remind ourselves that we're talking about homotopy zero types, because we previously remarked last time that S1 can be characterized as the suspension of 2, okay? That's what we're doing here, where 2 was the 2-point thing. So this is a set, everything inside is a set, but we know that this has structure beyond a set, meaning that there are there's more than one path between any two elements of that type. Well, in particular, there's more than one path from base to base, right? And so we previously discussed that. So the interesting fact is that the homotopy type goes up when you form the pushout. Now, in a certain way, it's kind of obvious, because, well, we deliberately jammed in another path that wouldn't have been there in nature, so to speak, if we didn't put anything else. We just shoved it in there. So it does certainly look like we're pushing up the homotopy type by putting in a new path, in the same way that with the suspension, we obviously pushed up the homotopy type by introducing equations that were not using higher inductive definition. So in a certain way, it's not so surprising. It's just that I guess we're sensitive to the issue when doing it inside of homotopy type theory. In other words, that we're bothering to mention this, So, because the whole idea about homotopy type theory is that equations are not boring anymore. Okay, somehow the standard logical story is that, well, x is equal to x. What else is there to say about equality? Whereas here in this setting, because of proof relevance, we have structure to the proofs of equations, and so that's a good thing. Okay, so this is sort of an example of something that we can do more broadly. So I think I'm going to run short of time today, so I'm not going to go through this in any detail. So I can just say this sort of illustrates a pattern, so which we can say may also define, because I want to get to something else. Sorry, may also define sort of quotients using higher inductive types. Okay, this is possible. So this is an example kind of a quotienting construction, at least for quotients where, of sets by what are called in the book mere propositions, or just propositions, or H-props, or whatever we say. That is, by relations that are H-props. That is, that have no where any two proofs, if they exist, are equal, right? So the idea is that there's at most one thing. So we can easily define that. So, like, for example, if I want to define A mod R, I can just put it in here as a higher inductive definition, then I'm going to have some things. So one of the things is that we want to say that I will call it Q of A, which is A mod R. So you can think of it however you like, but it sort of says everything in A is, you can think of this as the equivalence class of A if you want, okay? Or it's not really an equivalence class because R doesn't need to be an equivalence relation, but anyway, there's a kind of an inclusion here, okay? And then there is, given A, B, and A, and a proof that A is related to B, okay? Then we have a constructor which witnesses well-definedness, so I called it WD for well-definedness. So that has as a function a D and R, if you want to look at it like that, which says that Q of A and Q of B. So whatever Q is doing, one can, and in fact it's discussed in the book, I'll get to that shortly, whatever Q is doing, it ought to be well-defined, okay? So it should take related things to equal results. So this would be equal in A mod R, right? If we wrote this down here, this would be equal in A mod R. And there's the last thing that I have here, which is if you have xy in A mod R, written like that, and we have P and Q, which say that they're equal in A mod R, then we have a thing here called TR, which I wrote, which is forcing things. Oh yeah, this is a TR standing for truncation, okay? And then that's what I'm going to talk about next. So this leads me into that, which is the truncation, which says that P is equal to Q in the appropriate type, that is that equality type. So this is, I don't know, this I might say is kind of expected, maybe. And here is a forced truncation, okay, is what is going on here. So we're saying that any two proofs of equality within the type I'm defining are equal. So what I'm really saying here is A mod R is truncated to a set. Okay, so that's a definition that we could give there. And so I could, and then the book characterizes, you can find out that in the book, you can look, I'm doing this one quickly, that if you look at the maps from A mod R to B, given this definition, given the requirements that are imposed by the definitions in higher inductive definition, what do you suppose this is going to say? The maps from A mod R to B are going to be the maps from A to B that respect R. Okay, right? That's what you would think. So we say for every A, B, and A, then we want to know that if A and B are related, okay, then F of A has to be equal to, in the appropriate type, F of B. And this would be B in this case, right? if I want to write in the type here, okay? So it's the well-defined maps. Now, the reason to bring this up is there's a further, it's a very pleasant read here, this section. There's a discussion of other ways of formulating notions of quotient, and I'm going to skip that because I don't have time to do it, but I do need to say something about quotients, which is forming sets of equivalence classes or looking at unique representatives of equivalence classes, which is many ideas that we, in informal math, we just kick around as being all the same thing, at least when R is an equivalence relation. And the book develops it very nicely in the context of the homotopy type theory to show the various equivalences that one would expect would have to hold. And I'm just going to leave it at that because this is the last lecture and I want to get to something else, so I want to do that. But the example that is going to be important here is that we can use, so I'm not going to give the details of this, but an example, one reason to bring up quotients is we can define Z, okay, to be some quotient of pairs of numbers in R, okay, like this, for a suitable R. And what is a suitable R? Well, it's the usual construction is we can represent them as formal differences of natural numbers. And there are different ways of doing it because you can choose canonical representatives and various, there are various ways you can set this up. But the idea is you can just think of an integer is a formal difference this is supposed to be it's really the ordered pair, just the pair mn, but we will write it as a formal difference of m and n, and then you can relate when our formal difference is going to be considered equal, which is r, which is m prime minus n prime, so this is some other pair m prime, n prime, and guess what? Two formal differences like that are equal when this plus this is equal to this plus that, right? I mean, as natural numbers, that's a standard thing. Okay, so you can do that, but we need Z. See, so that's the reason we need Z in a minute. That's why I need to bring that up. Okay. Okay, so now the next thing that I wanted to make, so you can do this, and the only thing that you may not have seen before, and I'll use it in a few minutes, and we'll just see it. In practice. It gives rise to an induction principle. For Z, which actually we introduced in lambda Perl, the beginning, before the predecessor to new Perl. New was the third in a line of attempted versions of Perl, going back to around 1980. And it gives rise to an induction principle. Once you write it like this, it's obvious what you do, but it amounts to distinguishing that the numbers in Z can be partitioned into three classes, the positive ones, the 0, and the negative ones. And there's an induction principle that says you can work everything towards 0, and if you work both sides towards 0, then it covers everything. I won't bother to write it all down, but you can do this, okay? But if you do it as formal differences, and you can see this in the book, it gives rise to an induction principle. The reason I mention it is we're going to need this. Shortly. Okay. Okay. So that's that. Okay. Now the last thing that I want to mention about higher inductive types before doing the last thing that I want to do, because the last piece I need are the truncations. And you can already see. Okay. I've been hinting at it already here because, for example, when I talked about this quotient, I did a truncation that was forced in here by hand. So what I want to do is, let me go back a couple pages in my notes. So what I want to do is go back and review the notion of the propositional truncation, okay, and view it as a higher inductive type. So the first one will be the propositional truncation, which we saw before, which we'll now write as A sub minus 1, because you remember when we discussed n types, we decided that the propositions, in this sense of the term proposition that we use it here, are those that are minus 1 truncated, meaning that if any two elements are equal, but if there are any, but any two elements you can find are equal. Okay, so that's what we're going to do. And so this can be defined now as a higher inductive definition, because so this is, turns out, we did it previously as a special case. We just defined propositional truncation, and that's just fine, okay, but it ends up, we're going to end up wanting to I'll need at least for today, the set truncation, and then one can in fact talk about the end truncations. And I won't have time to go into any of that, but we'll do it here. So this is again a higher inductive definition. So the notation that's used in the book, I could, if I wanted to, I could put a -1 there to be like emphatic, because I'm going to need two notions of truncation at once. Momentarily. So we have an inclusion. So it sort of says, you know, everything. So they think of this as an inclusion, or an insertion. In other words, we insert everything in A, gets inserted in here, but then we impose the requirement. I think I called it squash or something like that. Which, and I think I want to say something about this. This confused me actually for a little bit, but it seems to be okay. All right, which is like that, which is the truncation really is what is being done here. So what we're saying is, so what squash tells us, right? So in other words, that is, we can write this out. What squash tells us is if we take any A and B, okay, and the point is that they're in the truncated type, okay, then that's going to be, your squash is going to be a witness that they're equal, okay? So it's basically just a way of saying that any two things that are in there, if you can come up with two things, then it will tell you why they're equal, okay? And so that's what's going on here. So at first I found this puzzling because, and that's one of those things, I guess maybe you will or maybe you won't. When I first looked at it, it looked a little funny to me, because I'm thinking, well, wait a minute, you're inductively defining the -1 truncation, and then you're quantifying over the -1 truncation in order to define the -1 truncation. And I thought, you know, isn't this like a negative occurrence of the thing we're defining? And is that a well-formed inductive definition? And then I asked Steve about it, and then he pointed out, which is really I think appropriate here. There is a difference in that it's forming a path, but it's really a lot like saying we have 0 in the natural numbers, and then for any natural number, there's a predecessor operation, successor operation, which, as it will work out there, is another natural number. So this is kind of saying, you know, give me any two that you're doing. It's closed under the existence of the following paths. And so if you think of it that way, then it doesn't seem strange. But somehow it struck me as strange when I first reviewed it. Not the truncation itself, but this formulation as an inductive definition struck me as a little bit strange. Okay. So now if you look at this, if you then take the elimination rule, the induction principle that comes from this, the point I want to make, the induction principle that comes from it, that arises as viewing it as a inductive definition, is, lo and behold, going to be the one we wrote down before. Okay, so it says, if we have, I write here, a family of types, so a predicate. If you have a predicate on the propositional truncation of a type, then, and for any x in A, you're going to see now, for any x in A, right? If I'm using kind of type theory notation, you have a proof that P holds of its insertion. So that would be written like that, right? So that sort of corresponds to that. And then what else do you have to do? Well, you have to know that for any x and y in the truncation, okay, and any proofs, you see, if you have a proof of P of x and you have a proof of P of y, then if you're, you know, because remember the general form of an inductive thing, induction principle is always going to be to reason away from, so something or other will be in P of z, right? So we're defining a map out of this guy, okay? So since there's an equation that's imposed here, then you certainly had better not have distinct proofs of P of X and P of Y. So there should be some Q, which is written here, which can be written as U is equal to V, but then we get the usual problem, okay? Those are different types, so we don't really mean U is equal to V. What we mean is that this is really over the path squash XY, which is one of the basic paths that you have here with respect to P up here. I write it as Z dot P, which, remember then, by definition, that means if I transport with respect to P along squash XY, and if I transport U along that, then I should get something which is equal to V, yeah. In this case, it'll be P of V because I moved everything over to the right, okay? And so I get it like that. Is that the correct formulation? I think that's right.
P of Y.
What?
The type is P of Y.
P of Y, yeah, because it's X and Y I'm dealing with here, yeah. P of Y is equal to U and V, yeah, the type is P of Y, yeah, of course. That's what I'm doing here, yep. Okay, and then you get a recursor and an induction principle. Just writing it down here, ZP. And then I wrote it out like this. I tend to write it in this form with having recursors. So X, Y, U, V, Q. It gets a little heavy. Okay, wait, if you think this is heavy, wait to see the next one. Okay, and then such that what? Well, let me not write them down, but such that you, on the 0 cells, if I run the recursor, apply this to if Z, in other words, if Z, so we should, this should be, of Z if you want to make it explicit. So this is of Z, so if I run this on the insertion, wherever it goes, the 0 cell will give me the appropriate instance of P. And if I app it, we talked about this before, that is if we look at what it does on 1 cells, which is given by the apply to paths, then that behavior will be determined by Q. Okay, so that's what we do. So let me not write that out. That gets a little messy. Okay, and so that's the idea. Okay, and if you specialize this to the recursion principle, that is, if you make this be a constant, think of this as a constant family. So this works like that. Okay, so this part, so mentally you can just kind of cross that out. Okay, then you get something simpler. This part, you basically just get this part P is in here, and this becomes a U equals V. There's no over involved because we're no longer working with a we're no longer working with a dependent family that's there. Okay, so that's the idea. Okay, so now the next thing, which we didn't do before, but I am going to need for what I want to do, is the idea of the set truncation. And again, this is, well, you could say as a hit, but actually I'd never defined it before, so it's the only thing I'm going to be able to do. So I can define now this guy, which is written like that, or the 0 truncation. So this is otherwise known as 0 truncation because we don't have special words. After 1 or 2, we don't have special words anymore. So that could also be called the 0 truncation. And so it's the same thing, only more so. And I'm sorry, it's going to be a fright, okay? But there isn't much I can do about it. So what should the 0 truncation be? It means restrict or constrain or I don't know what, constrain or truncate, whatever word you'd like to say. You basically restrict A to be a set. And generally, okay, that is homotopy set or a homotopy 0 type, right? And so how does one do that? I want to ensure that there's at most one equation between any 2 elements. So I'm going to allow you to have many elements as you want, and they may or may not be equal, and they may, but if they are equal, they're equal in at most one way. Okay, that's the idea of the 0 truncation. So we can specify this as follows, is that we can have, again, the inclusion. So we start out by saying everything is in here. And remember that I should have said this before, but we can emphasize this again. Remember that all the maps in the theory are functorial, right? So this is not merely saying that the zero cells are included in here. I mean, it is saying that. But moreover, the action on paths, right? This will have an action on paths, and so paths in here will have to be included in here as well. Okay, so that's like a one thing. So that's you have to remember that. Like sometimes it can be easy to overlook that until you're familiar with it. That often cases, more is being said than you quite realize until you consciously remind yourself, or you get used to it. So that's really saying that, you know, everything that ought to be there is there, okay, is brought across the mapping here by this inclusion in terms of the paths. And then I have to kill off the things that I don't like, okay? So there are a bunch of things that I don't like for some reason, okay? So I'm going to do this, okay? And, oh yeah, there's something I should have mentioned before. This will come up later, which is that Z is a set. And this is a theorem. You have to prove this. And the reason that's important will come back to me in a minute. Okay. And now it says if you take any two elements of that thing, and you give me any two reasons why they're equal, they're in this zero truncation x and y, then I want to demand. Okay. So I called it squash again. That S squash of x, y, p, q, so this should look familiar. I could have called it trunk, says that p is equal to q where, well, let's do this once. Okay, obviously this gets rather heavy, start writing it down like that, but let's write it down once like that. So this is the squash or truncation, if you want to call it that, to forcing the two paths to be equal. So we've seen this before, you see, because it's a lot like that. Give me two elements and give me two proofs that they're equal. I'm going to forcibly insist that those two things be equal. And then this gives rise to a horrendous looking induction principle if we do this. So this part is not too bad, but when you start writing out what the induction principle is, well, okay, hold on to your hat. It's one of the worst ones I've seen. I've actually personally written worse inference rules in my life, but this one's pretty bad. Okay, sometimes things get carried away for you. So we have to be able to say there's a proof, okay, for the insertion. And again, to remind ourselves, whenever I'm specifying a mapping like that, it's implicit in homotopy type theory that this is a functorial dependency, or it's a infinity groupoid homomorphism, one could say. So all of the paths that are present in here are respected by P. P is a genuine mapping from A into here. So one has to think about that. Okay, and then we have, then we have the horrible thing, okay? I'm just following my nose here, but for the heck of it, I thought I would write it out. So if I have Z, which I called it Z, let me stick with whatever I called it. If I try to change the letters on the fly, then I'm going to be in big trouble, okay? So now I have that much, okay, that's good. So we're sort of kind of in the neighborhood, all right? So now we really get rolling. Now if we know that P and Q are proofs that X is equal to Y. Let me not write the subscripts. If you think it looks bad now, wait till you see what happens if I do that. And now if R is a proof that Z is equal over P to, in Z dot script P, I've been writing it here, W, and S is a proof that Z is equal over Q in Z dot script P to W. With all of that data, then we have some other guy. Here I called it Q. That was rather unwise. Let me call it SQ. Okay, and let me not give all of its arguments. It's a proof that P is equal to Q somewhere. Okay, and where's the somewhere? Well, it's in the this constructor. Let's call that one TR to avoid being. Let's call that one TR to avoid being confusing, because I see I didn't do such a good job here. So we do X, Y, PQ, PQ I think it is. Already I'm nervous whether I did this right, but I think that's right. You do that, and then, then you get a map out of, okay, so I know already your eyes are glazing over. So So I won't belabor the point. But the idea is this is what you get. That's what I care about for right now. If you take this as a higher inductive definition, this is what happens to you, okay, when you form the induction principle in the obvious way. That is, there's a usual way of inducing, like I illustrated here, of inducing the recursion principle, and then there'll be some equations that on the zero cells we typically take as definitional, and then we have an action on paths, and et cetera, et cetera. Okay, so we can write all that down, and this is the big monstrosity you get. So thank God for path overs, because if I didn't write these with path overs, it would be totally inscrutable. There would be these transports all over the place, and you would be like, yeah, right, okay. So that's the induction principle you get. Okay, but the main point is we're restricting this to being a set. Okay, that is the thing that we want to do. So you can imagine now if God forbid, we should try to write down by hand the groupoid truncation, the one truncation of something. Well, you would know what to do. Okay, but then I would probably be scrolling so badly that no one would know what was going on anymore. You can only just do it formally somehow. You would start to I think you would start to lose track of what the hell is going on. Even though you know what you're trying to do, it does get a little out of hand. So, but for now, let's just leave that topic there. That's discussed also further in the book. You can look. Don't have time this semester to go into details, but there exists a notion of the restriction to a set. And in fact, if you use that induction principle, we can show, therefore, this is true in general, but it's certainly true here. If I take a set and I zero truncate it, so in particular 0, then that is going to be that nothing happened, okay? So what this means is that a way of saying this is, saying it's a set, I already said it, and then this falls out, but whichever way you like to think about it, you could say this, you could take that as a definition of what it means to be a set if you wanted. Okay, but the idea is that there is no higher dimensional structure. In other words, there is structure at the zero cells. You have numbers. You have all of the I almost said natural numbers. All the integers, and the integers are all there. And two integers are either equal or they're not. It's a set by Hedberg's theorem because the equality of integers is obviously decidable. So it ends up being that there's no path structure going on. There's no non-trivial path structure. And then it's the same, and then all the way up it's degenerate, okay, for all higher dimensions. So it means it has no higher dimensional structure. So this is going to come up now for reasons, because the thing I wanted to finish up with is a very pretty argument involving the fundamental group of the circle. So that's what I want to do. And that seems like a very nice, way to finish up, because it uses, we're going to end up using a bunch of ideas that we've developed until now. Quite a few of them show up here all together, and so that's kind of a nice thing. Okay, so we hinted at this before. I just want to show you what's involved in the proof of this thing that I hinted at earlier in my lectures. So let's remind ourselves. Okay, let's remind ourselves what we're doing. Okay, so the main thing what we're going to do is we're going to consider what is called the fundamental group of S1. So that's what we're going to do here. And what is the fundamental group of S1? Well, let's remind ourselves what S1 is. So recall, just to remember. Of course, I can do it via suspensions, but I'll just do it here. Recall X1 has a higher inductive type defined by, it could be thought of as a suspension of 2. We've already discussed that, but let me just remind ourselves. We'll just do it say by hand. So it has a designated base point, and it has a loop between base in S1 and base. It's written like that. So the obvious picture is that we have the base point B. There's always a little reflexivity guy, and then we're throwing in another thing which we're calling loop. Okay, written like that. So it looks kind of circular, so it seems like a good thing. All right, so that's what we do. All right, so that's the idea. So remember, the loop is an equation, right? This is saying there's another reason why base is equal to base other than the fact that it is, so to say, that it is by reflexivity. And so it's a nice example of proof relevance, right? This is telling us about proof relevance. You know, as I mentioned, you can think about these things in different ways. If I tended to write this as ID sub S1 of base, which is of course the same thing, it feels more like data. And when I write it using kind of logical notation, it feels more like a proof. I don't know. So it's just what I was saying many times. So the idea is that the proofs are relevant, that what we're interested in doing. Okay. And then the other thing we want to look at is the loop space. So the other thing we recall, and we'll do it like this, the loop space. And it's often defined for a base type, but we can define it with respect to a base point, or you can think of that as a base type, whatever you like to do, right? This is, by definition, it's just the identity type. It's just the type of all of the proofs that A naught is equal to A naught, okay? Or in other notation that looks like that, so we think of that as data. So that's the definition of the loop space, okay? And so that's the two things, so we've talked about that before, okay? So this says, consider the type of all the paths that start and end at A0, okay? So what we're interested in studying is, or by definition, the fundamental group of anything, fundamental group of A, of any type A is defined as follows. So what I want to do is I want to look at, well, okay, you could say at A naught, or sometimes people have implicit a base point. So that's one of those things. Okay, so let's say the fundamental group at A naught, we could look at it like that, or else we could form the product of all of them. But anyway, let's just say it's at A naught. Okay, what is the fundamental group going to be? Well, that's really, it's written like this. You take the loop space of A at A naught, and then you form its zero truncation. And this thing is called, by definition, this is called pi1 of A naught, is by definition the thing that I've written there, the truncation, the zero truncation, okay, of the loop space. Now, why is it called pi1? Well, because one can actually consider the higher homotopy groups writing pi n, which are saying something about the higher dimensional loops, in which case you would n here, what is supposed to be correlated is pi1 is loop space to the 1, okay? That is, I've iterated it one time, I didn't iterate it at all, okay? And you can actually write pi n here, so this is the point. The 0 is not what, it doesn't have anything to do with the fact that it's called 1 here. I'll get to the 0 in a minute. It's this one and that one are the same. So you can write pi n, which is the iterated loop space, which is the loop space of the loop space of the loop space of the loop space n times, okay? So that's why it's called pi1, because there actually is a more general thing, which is pi n. So the important thing is that we know in general, right, that any type, including the loop space, is going to be an infinity groupoid. Okay, so that's the first thing. This is going to be a pointed type because we can think of there's a pointed type is having refl 0, or refl A0, excuse me. Refl A0, okay, is going to be its base point. Okay, you can think of that as the designated base point of the loop space. And so what's happening here is, I lost my thread. Oh, okay, which is the idea is that that this has the structure of a groupoid, but we want to truncate it, so this forces it to be a group. And what do I mean by that? Well, you have to get used to that in a minute, for a second, which is, I didn't really go into the definition here. But the idea about a group, as you know perfectly well, is you have a set together with some operation, a multiplication, and an inverse, and an identity element that satisfies some equations, okay? And typically those equations, and you know what they are, and those equations hold on the nose, so to speak. Well, in a type theoretic setting, those equations correspond to paths, that there exists paths like an associator path, and there exists an inverter path, right, that tells you that the inverse, the thing that you're calling the inverse is the inverse, and so on. So you can write all those things down, but then the thing you get is not necessarily a set, okay, because it has higher dimensional structure. It's got paths all the way up, okay? And so then you're getting something else which is called a higher group. So if you want to reproduce like what is typically done, like the definition of the fundamental group, for it to be a group, okay, we want the whole thing to be a set, so we truncate it, okay? So in a certain way, what's happening here, there are several things you could like feel, you know, like you could wonder about, and those are all good things to wonder about because all this can be generalized in many ways. But one thing you can wonder about is why stick to base types and why am I considering only loops? One can consider that. But you can say, one thing I'm saying here is that in a certain way, it's a weak thing to study the fundamental group because you've by definition killed off all the higher dimensional structure, and you say I'm blatantly ignoring that. Okay, that's like don't even ask. Now it turns out for the particular thing I'm going to do, we're going to be able to say something about the higher dimensional structure. It turns out. So the classic sort of textbook, chapter 1 theorem is so the theorem that we're sort of shooting for is that if you look at the fundamental group of S1, that should be Z. Okay, so that's the thing we're looking for. And we talked about this before. So, and I'm going to now spell out exactly how that works. So it's kind of nice, and the point is the argument is completely straightforward, and it uses all of the tools we've been developing, so it's a nice way to end up the semester. So that's what I'm going to do. Okay, so the idea that this is E. So remember that this is already a set, right? So we didn't have to worry about truncating that for the thing that I inconveniently erased over here. But what is it saying? So there's an equivalence, okay, between two sets, okay? So with respect to the path structure, there's not a whole lot to say. We'll see that. We'll exploit that because between any two elements of any set, this is definitely a set, this is a set, there's at most one proof that they're equal. So the action is really in the elements in some way. And so what's happening is we're saying, well, if you look at all of the ways in which I can get from the base point, that is base, which I called it here, back to myself, it's kind of obvious that, well, I can go around and go back around because these are always invertible. I can go back around and do it any number of times I want, including 0. And somehow that should completely characterize what's going on, at least as far as the restriction to a set is concerned. Okay, and then one can ask other questions. So it's actually going to be possible to prove. So what we'll actually show is that is we don't need to even worry about the truncation. We can just look at the loop space of S1 at base, and I will just abbreviate that. The loop space of S1 is going to be equivalent to Z, full stop. That's the thing we're actually going to prove. Okay. And then it follows, if I do the 0 truncation of the left and the 0 truncation of the right, that those two will be equivalent. That's just an easy thing to show. The 0 truncation of this is, by definition, the fundamental group. The 0 truncation of that is Z, which I mentioned before, can be proved separately, so we get the theorem. So what we actually show is this. Okay? So in this case, we're saying something that is stronger because we are and we aren't. The point is that the theorem is a very simple case so that nothing hard happens. But in a certain way that, what we're saying is the whole higher dimensional structure lines up with Z, and Z doesn't have any higher dimensional structure, so we're saying that's the way it works. So that's what happens. But in some sense, formally, what we're showing is as types, okay, these are equivalent. I don't even need to restrict, I don't need to restrict attention to just the low dimensional part here, okay? So how do we do this? So it's very simple. The basic setup is very simple, and then I'll show you how this goes. So the first thing is we want to define a map. We're going to define maps in both directions. So we're going to define a map and then show that they're quasi-inverses, because that's the typical way we do this. So we're going to go from here, and then I will just always write loop space of S1 with the base point being implicit. So what am I going to do is I'm going to define a map from Z into here. And what is that thing going to do? Well, I want to take a number and turn it into a loop. So what I'm going to do is I'm going to have this kind of loop to the n thing. So I'll write it like that. Okay, loop to the n is defined by induction on n. Okay, or well, n being an integer now. So that's the important thing. Okay, so I will use Blackboard notation here, and you can turn this into a use of the recursor for z, which is why I made that remark earlier. So the 0 times iterated loop is going to be reflexivity, of course. Reflexivity at base, and I'll probably often just say reflexivity, okay, but reflexivity at base, okay, like that. And now you get to do this thing, okay, about positive and negative numbers. So if you're looking at a negative number, that's my Blackboard notation. You have to make this all the same. Then what is this going to be, right? It's going to be loop to the minus n plus 1 dot loop. I think that's the form I wanted, okay, to doing it like that. And then this would be a loop of, if you don't mind me writing plus n to remind you, okay, then this would be loop of plus n minus 1. That's just a reminder, okay, dot loop. Okay, I hope I defined it the right way. Did I do it wrong?
For minus n, you want loop inverse. So
What did I do?
you said dot loop.
Yeah.
You probably want dot loop inverse.
One of them should be inverse. Yes, you're absolutely right. This one should be inverse. Yes. This should be inverse. Yes, you're quite right. Yeah, that should be loop inverse. Let me check ahead in my proof. Somewhere in my proof, in order to make everything work smoothly, I wanted it to be that way. Yeah, okay. I wanted it to be that way. I could just as well have defined it as loop inverse dot that, and then it would have complicated the argument. It wouldn't change it really, but it would have meant I had to do something. So I think if I do it this way, everything works the most smoothly. But knowing me, okay, maybe it didn't. We'll see. Okay. All right. So that's that. So we just defined that's the obvious thing. So that just says take a number and make a loop that goes around that many times. But remembering that the number can be negative, so it can mean going around backward. Okay. So you can turn this into. This is really defined by, Z recursion. And I didn't actually put that on the board, but you can do that. So I'm expecting you to accept that that's a good thing. So now I want to define what will be its inverse, which I'll call winding. Okay, and what does it do is it takes something in the loop space and gives you back a number. Okay, and then eventually I'm going to prove that these are quasi-inverses. So how do we define the wind? So this is the winding number, okay? And it's exactly what you think, but let's see how we define this. So the main thing is this. Is first of all, so there's 5 parts that I have here. Okay, so first of all, the successor, remember that the successor is an equivalence. Okay? In other words, it has an inverse. In other words, we have successor going from left to right, and it has an inverse, which is successor inverse, which I will also call pred. Okay, is implied here, and they're inverses. I know it's shocking, but that's the lemma we need here. Okay, so that's the important thing. So we have an equivalence here. Okay, and because we have an equivalence, then by univalence we have a path in the universe. So the point is I can take UA of the successor, and that's an equation. That's a proof that in U, Z is equal to Z. Okay? So here I'm using univalence. Okay? All right? And then, all right, so that's so we're going to need that little bit of data. So that's going to be quite important, all right, that we have a way of representing that. So UA of successor is a path from Z to Z. okay? And so if you start concatenating these UAs of successors, right, because these are paths, you'll get longer and longer paths from Z to Z, which are encoding, for lack of a better word, encoding the successor equivalents, okay, between them. So it's a way of saying what's going to happen is the underlying thing that's happening here is that this says that there's an equivalence, and the equivalence is going to be given by bumping up all the numbers and bumping them all up again and bumping them all up again. And you'll still have Z because there's an infinite supply in both directions. So that's why that will work out. Okay, so that's how that works. Okay, and then we define this other function, which has various names, which could be called the cover, or in the book it's going to be called code. So we're going to define this function called code, which goes from S1 to U, is defined by S1 induction, S1 recursion, okay, as follows. Okay, so here's what I'm going to do. What I'm going to do is I'm going to send, and now here's this notation we've used a few times. Let me write it like this. I'll say code of base is defined to be definitionally, what is it going to be? It wants to be in Z, so in U. So what I'm going to do is I'm going to give it a type, okay, which is Z. And then using this informal notation we've used before, I now have to say it does something on the loop. And remember, we talked about this. I'll write colon equals here to say, by definition, it is going to be what I did a moment ago, the univalence axiom applied to successor. So we do it like that. So remember, what does that mean? What it means is that code is given by a recursor. The recursor on 0 cells will definitionally validate that equation, and the action on paths, okay, of the recursor when applied to the loop will be up to higher equations, the one that we designated before. So that's the notation I've been using, just to remind you. Okay? Yes?
There's a small gap between the dependent path over a constant family and the regular path.
There's a small, okay, say that again, please.
So the right-hand side gives you a regular path.
Here.
Yeah, right, the last line. The right-hand side gives a regular path.
Yes.
And the left-hand side,
regular path.
the left-hand side requires a...
That's a path that's written in here. Yes.
Right, and the left-hand side requires a dependent path over a constant family.
Yeah, well, that's why I said it's by recursion, not the induction.
Oh,
Okay, so we previously talked about when I did this thing, I did a recursor and I did an inductor.
Right, I mean,
Okay, so in this case, that stuff is factored in already. Okay, so that's why I did it like that. Okay, yeah, so that's what I meant there. Okay, so that gives us that. We're going to use code in a minute. Okay, but the important thing is, remember, we're trying to get over to here. So what we're going to do here is we then take app of code. Okay, and what is app of code, the action on paths of code? What is that going to be? Well, first of all, let's write down its type. It's going to go from the loop space of S1. Well, why is it going from the loop space of S1? Because by definition, this says base equals base. Base in S1, base. So the domain of code, right, is S1. So when I look at its action on paths, it's given here like that. And that goes over here to Z equals U Z, okay, which is written like that. That's just a remark, okay. This is a fact of previous, so we can say recall here or something. That once I have code written like that, that's what the action and path is. So that's the important thing, is it takes base equals base, well, more generally, but we'll just say base equals base into here. And then E, what we do now, we define winding. What is the winding number of a path P? Okay, a path P now, blah, 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 is going to be in here. So it's really a loop. I could have called it L maybe. Okay, is by definition, what do? I take what is called the transport. It's a little tricky here in the identity function of the action on paths of code. okay, applied to P, that particular loop, and then I make that and do a transport on 0. So what the hell is going on here? Well, what's happening here is that this you can think of is it extracts the underlying equivalence. Because if you look at what transport is, and you look at unwind everything that's going on here, then what's going to happen is this thing is going to work out to be UA of successor, actually some iteration of that. But think of the case where we're doing the loop. This will work out to be, the action on paths will be UA of successor. And when you transport in the identity, with respect to the identity family, what it's doing is extracting the underlying equivalence, namely the successor, from the path, which is this UA of successor, and then applying it to 0. Okay, so that's the idea. So it basically says this path P, remember winding of P is here in the loop space. So P, in your head, what is clearly the case is this is some number of iterates of loop in various directions. But anyway, it's a general path in this space. And so what I do is I take this action on path that I talked about before and then use a transport because that will induce, right, some kind of a path between Z and Z, which is the one I alluded to earlier. And then you so to say, extract the underlying equivalence, which will be successor, and apply that to 0. So that's the idea. So it will give you, so the point is that I'm trying to show how in homotopy type theory your perfectly evident informal argument, how does that really work? And so I think it's rather nice to see how that all works. Okay. Okay, make myself some room. Okay, so that's what's going on there. So now we've defined, so I claim now I've defined the winding number. So I've defined this iterated loop thing and I've defined the winding number. Okay, so now I have two obligations. Okay, so first of all, I have these two quasi-inverse things. So one thing I want to do is for any n in Z, right, I need to prove one direction, which is if I take the winding number of the nth iterated loop space, okay, that should be equal in Z to n. Okay, so that's the first thing I need. I'll say something about that in a minute. And then the other thing I need is for every, let me get my letters right, for every, I called it L, so let me, it's always important that if I stick to whatever notation I did, otherwise we're definitely dead. So if we take the winding number of L, okay, and then iterate the loop that many times, that in the loop space of S1, that should be equal to L. Now, if I can do that, if I can fill in those two things, right, then I will have established, okay, I will have established the required equivalence because I've given you maps in both directions and shown that they are quasi-inverses. Okay, so I will be done. That's the important point. All right, so you're with me? So now we're just following our nose. What is the definition of quasi-inverse? Okay, so this one is quite easy. Okay, I won't write the proof here because it's quite easy. You can prove it right here. It's quite easy to prove directly. To prove by induction on n. Well, let me emphasize, Z induction on n. Okay? But the idea is, right, so if n were 0, then loop to the 0 is by definition reflexivity. If you look what winding is, it's saying do some action of path on reflexivity. So that's a reflexivity. What does TR do on reflexivity? Well, it's basically reflexivity, and so you end up with 0. the identity. So you can end up with, 0, and then you can do an easy induction. It'll fall out of what we do a little bit later here, but we can do this. So it's kind of fun if you want to do it for yourself. So there are 3 cases. N equals 0, n is positive, and n is negative, okay? And you can work out the calculation. So that turns out to be very easy. So it's kind of certainly it's what you would hope for. If I iterate the loop n times, and if the winding number is supposed to be the winding number, then that really should come back with n. So the trouble is all here, okay? This is where this is difficult. So this is more difficult. Okay, and let's just see why it's more difficult and how we get out of trouble. Oh, it's more difficult because we're thinking about the loop space. I'll just remind ourselves, this is base equals, by definition, base equals base. Okay? So your idea would be is you do a path induction. It's the only thing you could think of doing. I mean, it's all that's available to you, really, on L. Right? This is what you would think to do. Because I've got a path in a space, okay? And I want to define a mapping out of it, okay, out of the paths in that space. And so if you're a little too facile, if you don't have a computer to check you might say, oh, okay, so all I have to do is prove it for, you say to yourself, it suffices to show, which you can tell I'm signaling that's not true, okay? You say it suffices to show that loop to the winding of reflexivity at base, okay, that's what that would be, is equal to reflexivity at base. And indeed, you think, well, that's probably, if I unravel everything, it's probably even just a definitional equality, okay? And so you think you're done. Okay, and then you're wrong. Okay, so it's a pity because it's almost completely straightforward like that. So what's wrong with my argument? So when I say I do a path induction on L, what I mean is this guy will be J of something. Okay, and the argument to it will be L, and it's supposed to be a proof of this thing over here. So that's what I mean by doing a path induction. So where have I gone wrong? Okay, this being the last day of class, I'm going to expect you to diagnose this. This is your final exam. So where have I gone wrong? Okay? No one knows? Yes, Ed.
The path isn't free?
Yeah, the path isn't free, okay? The problem is this, is that what path induction lets you do is you reduce a fact, like, remember you say you reduce a fact, you want to, let me write it in the most, abstract sketch form to remind you. It lets you prove a property of what? P, M, N, and Z, right? That's what path induction lets you do. Okay, the form of path induction is that. And the sufficient condition, it says, is that if you give me any x in A, it suffices to prove P of XX REFL. Well, REFL of X, okay? Written like that. This is generic, okay? This has to be generic. Okay, it's important that it be generic, okay? Now, it's true that for S1, if I say to you, name a point in S1, there's only one answer you can give me, which is base, okay? That's the only point you know about, okay? But I have to be able to do it generically for any point, in the case we're considering, it's going to be S1. So I want to get something about, this is base, base, and S1, and I want to get something at base, base, and Z. That's what I'm trying to prove here. That would be the idea. Okay, it's base equals base. Okay, so I want to do this. Okay, So you feel like, so if you could do this part, then you would be good. You would actually be able to instantiate it. But the problem is you're not going to be able to do this part, at least right now. Something else has to happen, because you need to be considering, it's not sufficient to consider it for base. You have to consider it for x. Okay? Of which base is one case where x is in S1. And now that's a little bit unnerving. So now it's not so obvious, okay, anymore. It certainly isn't going to hold definitionally, okay, whatever happens, right? It's not going to be a definitional equality, okay. So what do we do? Okay, so do you see the point? So this happens quite a bit, actually. We had something similar to this when we talked about the characterization of paths in a sum. There it was slightly different. It wasn't completely free because we were trying to say something about paths of the form in left and in left, and that wasn't completely free in the paths in the sum space. And so if we want to do an induction about, you have id in left of m, in right of n, and you want to say something about all such paths, the path induction that you want to do is not immediately, it's not immediately obvious you can do a path induction there, because the endpoints are not completely free. You're saying, oh no, only those for which they're in left of m and in left of n. Okay, that's the thing you're interested in, but to apply induction you have to consider all paths. So that's what we did before, and we defined a family, and we showed, and it basically amounted to the fact that we could define an inverse definitionally for the in left, and we could make the whole thing work. Okay, well, there's a similar kind of thing here, okay, that you get into trouble. So what do? Well, you do what you always do. You strengthen the IH. So, by the way, I'm presenting this in the style that, you know, this is like a CS style proof, you could say. There's another sort of argument, which is a repackaging of what we're doing, that superficially looks different, that many of you probably know. And my point is just to present it in this other style that I find natural. Okay, so here's the idea. So the thing I have to prove is here. Okay, and this is actually so what I do is the following thing. What I do is I define two functions. So we strengthen the IH. So what we do is we define, and now these have become always called encode, because remember we defined this thing called code before. So we're going to use this guy. So we're going to use this. And this could also be called a cover, for those of you who know about that. Okay? So that's what's written here. It's basically a cover of S1. Okay, so what I'm doing is, so I'll define encode. And what encode has the following type, S1. What does it do? It lets us do a based path induction. So we discussed this before. You can get a form of path induction in which one endpoint is free. That's good enough. Okay? That is fully general, so we can work on this. So we can define it like this. So we define this, which is code of x, okay, like that. And we define decode, which takes x in the S1. So the point is the for all x's now here. And this goes code of x, arrow base equals x. So, and then what we do is we show that these are inverses to each other. That is, for every x, you know, for each x, okay, that these mappings form an inverse to are inverses to one another. So let's say we can do that. So let's say we establish a pointwise equivalence between, for any x, base equals x is equivalent to code of x. So if you plug in base, and you look at what code of base is z. Okay? So I will then plug in base, and then I will have an equivalence between base equals base, the loop space, and code of base, which is z. So I will have an equivalence between the loop space and z. And I'll be done. Okay? So this is the idea. So it's just strengthen the IH. Okay, so now let's see how we do that. So then we're in good shape. Oh my God, I'm out of time already. I can't believe it. Will you allow me a few minutes to go over? Okay, so let's define what this is. You know, I honestly thought I was going to finish early today, so that's really insane. Okay, so what is encode? So it's defined like this. You take lambda x, which is in S1. So I'm not going to get to go through this with you. That's a pity. But actually, the main ideas are going to be there. So, and let me write it all out. This is base equals x. And what you do is you transport along the family code, which I've written here because code is p to u1. So along the cover, I transport by p and run that on 0. So therefore, we notice, okay, if you wish, that winding of p, as I've defined it before, winding of p is then going to be the encode. This is a more general thing, is encode of base and p. That just, you'll just notice that by the way we defined it before. So that's what I do here. And then for decode, which goes the other way, so what does decode do? Let's find this here. Oh yes, this is a little tricky. So this is the kind of thing that comes up a lot, even in functional programming settings. Like with GADTs in Haskell is based on the following mistake. Okay, so the idea is that you might think, oh, I'll just blithely go lambda x, lambda p, base equals x. That's what this is, and then figure out what to do here. Okay, and it's not going to work. So in Haskell, what they do is they let you write that code, and then they kludge it up with the type checker to cover up your mistake. So what you want to do instead is this. You don't want to be doing the lambda abstraction too early. Okay? If you do the lambda abstraction too early, then you won't be able to push through the argument. So I don't have time to give you everything that's going on here, but this is what happens with GADTs and why they have this crazy-ass type checker that does all sorts of random things. It's because it's the wrong thing. Okay? So what you do is you do an S1 rec here. So let me call it specifically S1 rec to remind you. So I do an S1 rec, okay, in the following type, in the function type. So let's call it Z. Code of Z arrow, just to kind of emphasize base equals Z. I mean, I could have called that anything, but I want to say the family, it's a family of function types. That's what's important, okay? And what I do is the argument to S1 rec is going to be lambda Z refl of base. And if you work out what that has to be, because of the dependent forms, you'll see how the dependent typing works out. And here we'll write lambda n loop to the n. And then we'll apply that to x. Okay? That's what's important here. So the critical thing, okay, is the typing that goes in here and checking that these types. You have to check these, okay? So you want to check these. So check the types. And the point is what you will see is what happens is the arguments get, especially here, the types of the arguments get specialized by the fact that you're in that branch of the recursion. And therefore, you define a function for the special type, not for the general type, which is what you would do if you did lambda p. So the problem is if you put the lambda p out here, x is now a variable, and then you have to do some crazy-ass thing to somehow specialize it into the context in each branch. That's what they do in Haskell by some unification tricks and mumbo-jumbo and God knows what. Okay, and then you call it GADTs and stuff. But really what it is dependently typed programming done awkwardly. Okay, so here it's the exact same example, okay, as what's going on. So the critical thing is you write it like that. So the lambda ends up inside, okay, in the case of the 0 cells, the lambda ends up inside here, and that's what you do. Okay, so I'm actually running out of time, and so let me just say something about how the proof works. So to finish, to show that these are inverses, you're going to need a path induction. I'm sorry that I'm not able to do this at the board, and a circle induction, an S1 induction. You'll need both of those to do that, so you should complete that, write that out for yourself. That'll show that the encode and decode are mutually inverse. I have a family of equivalences. I specialize it to the only point I know, which is base, and I get the desired theorem. Okay? And that's it. So critical coding trick, is right there. Okay? Don't be too eager to put your lambdas down just because the type has to be an arrow. Okay? So that's what is happening here. Okay? So that's critically important. So you do that, and then you're golden, and then the whole thing works. Okay, so I've run over time. I'm sorry I can't show you the details of that. Once I've set everything up there, as usual with these kind of inductive arguments, the hard part was figuring out, it wasn't even hard here, but in general, the hard part is figuring out the stronger thing you have to prove. And so this is the stronger thing you have to prove. And then in the book, there's a nice discussion of relating everything that's written here. You can re-parenthesize the argument and put it into the form that is more of a textbook form involving the universal cover of S1. And you can have a look at that, and that's actually very pretty. So it gives you a flavor now of like the kind of things one might be interested in saying. And in fact, in the rest of that chapter, there's that I'm referring to in the book, is a development of a bunch of theorems of this sort. That is, what I mean of this sort, characterizing the paths that can arise in a space in various ways. Okay, let's not go into exactly what they are. And the thing that's fun is, it's all functional programming. Okay, so in a certain way, the thing that's beautiful about the subject is I don't want to, say this with my tongue in cheek, you don't even have to know what you're doing. you just write out the code and you just say, oh yes, I don't know what the hell, but I know how to program. So you write the code, and because propositions are types and proofs are programs, you write a functional program with the right type and you say, oh, it looks like I proved a theorem. Okay, and so it's cool to do that. It's kind of fun. So we've all been enjoying that. I suspect that the mathematicians involved have enjoyed seeing a computer science point of view. I know that I've enjoyed the other way around, and so I hope you'll enjoy pursuing it all further. So this is the end for us for this semester. So thank you very much for your attention, and have a good holiday.